How are you doing, guys? It's Emil here again. Today we're going to go over the non-collinear portion, non-collinear spin orbit coupling portion using VASP underscore NCL instead of underscore STD. So, we're going to change our directory backwards. We're going to make a directory called non-collinear NCL. Change over that directory. From our collinear calculation, where we got an, our density of states, or maybe you want to do band structure, whatever you wanted to do. I'm going to copy over our OUTCAR, our POTCAR, our K points, our INCAR, and our job file. Now, when you go to job, it's not going to be, if you're running Slurm, right, maybe you don't have a job file, maybe you just have this, or whatever you do, all you change here is VASP STD to VASP NCL. So I'll adjust that accordingly here. The second portion that we're editing is the INCAR file. So all you do is you're going to add in your spin orbit coupling. That looks like this, right? However, one small caveat is it's going to be a little bit more complicated. So we're going to go over to the previous URhGe calculation that I did, J0.51. Spin orbit coupling, INCAR. I'm going to copy it over this line. Go back to my own INCAR, and I will paste it here. So what is particular here is that we're breaking this down into its X, Y, and Z components for the magnetic moment. So we have 4 uranium atoms, XYZ, 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 XYZ. We're only focused on the Z component, or the C axis. This is decided from experimental that this is the easy magnetization axis, so that's all I'm going to focus on. Likewise, we're not adding anything for the rhodium or germanium atoms. 8 times 3 is 24, 24 times 0. The second portion that we need to focus on is this S-axis component. I'm just going to copy this all like that. You can see that for the most part it stays the same, but we need to add, usually need to add iCharge equals 11. If you want to delete a whole line, escape DD. We'll do that. Let's just make sure everything is correct. So charge density, S-axis, spin, anisotropy, however you want to pronounce it, and just make sure that it's consistent. Maximum 0. So you don't want the wavecar at all. If you want to probe your magnetic anisotropy, you could change the S-axis however you see fit. I'm going to keep it to C. I mean, technically, you're supposed to do it differently and see what the, most optimized, most optimal state is. And I refer to that here as well. So I'm going to change this maybe to 0. Yep, 1 there. And that's pretty much it. So again, not difficult. If you want, you could re-optimize. However, I don't believe it's needed. And that should be it. And I'll tail it here just to make sure. Ah, okay. So I forgot to copy over the charge car. Let me double check. Yes, charge car. Now it should be working just fine. And this is going to be considerably slower. So I will finish this up, and once it's done, I'll check back in, but it looks like it will start without any problems. So we can see that we've reached convergence pretty easily here. And just looking at the OUTCAR, you could see that we have a ferromagnetic ordering. Magnetic moments on the uranium atoms are 2.252 each. And now, let me check this is noncollinear. All right, so I'm going to copy the DOSCAR over to the following. I'm also going to have to do VASP run.xml because to my knowledge, my density of states plotter, the GUI that I usually use, does not support non-collinear calculations. It gets pretty messy, like the DOSCAR file. So SUMO, they use the VASP run, and that's usually pretty good. I'll get the POSCAR in just in case. All right, so our folder's all downloaded. So I'm going to navigate over to it. Actually, I'll just do this. Conda activate ML project. That's my Conda environment. And I have SUMO. I think I've mentioned this in a previous video. Pretty much you just type this in like this. It's all in your terminal. And there is our density of states. So I've done edits to the code that they... Ooh, that's why. Okay. Hold on. Forgot. Yeah, so I did edits to their code. That's why this looks pretty wonky. Now that should work. Usually it just generates the density of states here, also horizontally, but there we go. I've adjusted it to be vertical. And yeah, that's pretty much it. So again, you're not gonna get your spin on these because we set iSpin to 1, or we just don't even include it. Let me double check, make sure. Ooh, okay. So this might be a problem. Make sure that you have this commented out in your preceding calculations. VASP should have thrown an error, but it did not. Anyways, and you can see the majority of the contributions above Fermi is going to be uranium. Below, it's pretty much high with uranium until -2 electron volts, whereas you're going to see rhodium take over. Predominantly the D states, high correlation. Actually, this is interesting. Equivalent contributions at Fermi level. Yeah. So, anyways, that's pretty much all you do here. And if you want to check out the SUMO documentation, it's right here. Their GitHub is also here. Next video, what do I have planned out? I will be going through the band structure, magnetic vectors. It should be pretty much it. So again, any questions, comments, queries, concerns, feel free to direct them in the comments or my email. You guys know how to reach me by now, I hope. And thanks for watching.